Hold out your hand. Look at it for a moment. That hand, those bones and tendons and skin, those fingerprints that belong to no one else who has ever lived, is made of atoms forged inside dying stars billions of years before the Earth existed. The iron in your blood was produced in a supernova explosion. The calcium in your bones was scattered across space by stellar winds. You are, in the most literal and chemical sense, a piece of the universe that has folded back on itself and become aware. A temporary arrangement of ancient star stuff that can hold itself up and look outward and ask where it is. So where is it? That question, pursued honestly and followed all the way to its end, leads somewhere that the human mind was genuinely not built to go. Not because the answer is unknowable. We know it with precision, but with measurements in mathematics and centuries of careful observation. But because the answer is so far outside the scale of anything our nervous systems evolved to process, that even when we say the numbers, even when we write them out and speak them clearly, the mind accepts them without truly feeling them. It hears the words and nods, and somewhere behind the nodding does not quite believe. Let us try to make it believe. You are standing right now on the surface of a rock, a spherical rock, roughly 12,700 kilometers in diameter, about the width of the United States, measured coast to coast, multiplied by about 4. The rock is old, 4.5 billion years old. It formed from a cloud of gas and dust that collapsed under its own gravity in the outer arm of a spiral galaxy, accreting into a ball hot enough to melt, cooling over millions of years into the layered sphere you stand on today. You live on its thin, cooled outer skin. The distance from the surface to the center of the Earth is about 6,370 kilometers. You will never travel that far inward. No human ever has. The rock orbits a star. The star is a medium-sized ball of fusing hydrogen and helium plasma, approximately 1,390,000 kilometers in diameter. If the Earth were the size of a marble, a glass marble about 1.5 centimeters across, the Sun would be a sphere 1.5 meters wide. Not a basketball, not a boulder. A sphere the height of a tall adult human, standing 162 meters away from your marble-sized Earth. That is the scale of the distance from Earth to Sun at this reduction, 162 meters. About a city block and a half. The Sun is the closest star to us. The next closest, Proxima Centauri, a dim red dwarf in the southern sky, is 4.24 light-years away. Light covers about 9.5 trillion kilometers in a year. 4 light-years is approximately 40 trillion kilometers. At our marble Earth scale, with the Sun 162 meters away, Proxima Centauri would be about 43,000 kilometers distant. That is farther than the circumference of the Earth. On a model where the entire distance from Earth to Sun is less than 2 city blocks, the nearest neighboring star is so far away it would need to be placed beyond low Earth orbit. Let that number breathe for a moment. Not because it is the largest number in this story. It is, in fact, one of the smallest, but because it is where the first rupture in our intuition occurs. The nearest star is inconceivably far away. Even when we compress the entire Earth-Sun distance to a city block, everything that follows only gets worse. On our Sun and Proxima Centauri are 2 stars in a galaxy. The galaxy they belong to is called the Milky Way, and it contains somewhere between 200 and 400 billion stars. Not 200 and 400, 200 billion to 400 billion. The number is uncertain because we cannot see all of our own galaxy clearly. We are inside it, embedded in one of its spiral arms, about 26,000 light-years from its center. The dust and gas of the galactic plane obscures much of the view in the plane of the disk. The Milky Way is approximately 100,000 light-years in diameter. Using our marble Earth scale, where the distance from Earth to Sun is 162 meters, the Milky Way would be roughly 460 trillion kilometers across. There is no analogy for this that works. There is no familiar object or distance that scales usefully. The galaxy on this model is so large that it extends well beyond the diameter of the observable universe itself. The numbers have ceased to correspond to anything the imagination can hold. Let us try a different approach. Let us shrink the entire Milky Way, 100,000 light-years of stars and gas and dust and the supermassive black hole at its center, down to the size of a dinner plate, 25 centimeters across. On this scale, where our entire galaxy fits on a plate on your kitchen table, where is the Sun? The Sun would be a microscopic dot, far too small to see with the naked eye, located about 10 centimeters from the center of the plate, roughly at its edge. Every star visible in the night sky would be similarly microscopic, clustered roughly in the same region of the plate. The nearest galaxy to ours, a small irregular dwarf galaxy called the Canis Major Dwarf, would be about 3 centimeters from the edge of the plate. The Large Magellanic Cloud and the Small Magellanic Cloud, the two satellite galaxies visible from the southern hemisphere as smudges of light, would be about 7 and 8 centimeters from the plate's edge respectively. Still on the table, more or less. The Andromeda Galaxy, the largest galaxy in our local group, a spiral containing approximately 1 trillion stars, stretching 220,000 light-years from edge to edge, would be about 60 centimeters from the center of your dinner plate Milky Way. Not far. On this scale, you could reach Andromeda from the Milky Way in one ordinary arm length. And yet, Andromeda is 2.5 million light-years from Earth. It is the most distant object visible to the naked human eye. If you know where to look on a dark, moonless night, you can see it as a faint smudge low in the constellation Perseus, a smudge that is actually a trillion suns, compressed by distance into a ghostly oval that most people mistake for a faint cloud. The light reaching your eye from that smudge left Andromeda 2.5 million years ago, when our ancestors were small-brained hominids walking the savannas of East Africa. Homo sapiens did not yet exist. Fire had not yet been discovered. The light you see from Andromeda is 2.5 million years old, and on our dinner plate model, it is 60 centimeters away. The local group, the collection of roughly 50 galaxies of which the Milky Way and Andromeda are the two largest members, all gravitationally bound to each other in a structure approximately 10 million light-years across, would be a region about 2.5 meters in diameter on this scale, roughly the wingspan of an adult with arms outstretched, 2.5 meters, 10 million light-years of galaxies compressed to arm span. Now we need a bigger room. The local group is itself embedded in a larger structure, the Virgo supercluster, sometimes called the local supercluster, a loose association of galaxy clusters spanning approximately 110 million light-years. At dinner plate scale, that is roughly 27 meters, nearly the length of a tennis court. In 3 dimensions, a structure containing thousands of galaxies on our model fits inside a sphere the size of a modest building. But the Virgo supercluster is itself just one small region of an even larger structure. And this is where the names become as grand as the distances they describe. In 2014, a team of astronomers led by Brent Tully of the University of Hawaii published a landmark paper in the journal Nature that redefined our cosmic address entirely. They mapped the motions of nearby galaxies, not just their positions, but the direction and speed of their gravitational drift, and found that the Milky Way, the local group, the Virgo supercluster, and dozens of other superclusters in our region of space are all flowing, very slowly, toward a single gravitational focal point. A region of concentrated mass that had been known for years by a name that captures something of its strangeness: the Great Attractor. The Great Attractor is not a single object. Yet it is a region of space containing an enormous concentration of galaxy clusters and dark matter and intergalactic gas, whose gravitational pull is tugging everything in its vicinity toward it. The Milky Way, along with all of its local group neighbors, is currently moving toward the Great Attractor at approximately 600 kilometers per second. We will never arrive. The expansion of the universe carries us along even as we fall inward, but the pull is real, measurable, and has been calculated with precision from the peculiar velocities of thousands of galaxies. The structure that the Great Attractor anchors, the superstructure within which our Virgo supercluster is a small peripheral component, was named by Tully's team using a Hawaiian word that needs no translation for anyone who has ever stood under a clear night sky. They called it Laniakea, immense heaven. Laniakea is a supercluster complex spanning approximately 520 million light-years and containing roughly 100,000 galaxies. Its estimated mass is about 100 million billion times the mass of the Sun. On our dinner plate model, where the entire Milky Way fits on 25 centimeters of porcelain, Laniakea would span approximately 130 meters. a structure the length of a city block containing 100,000 galaxies, each of which contains hundreds of billions of stars, each of which is itself a sun. And Laniakea is not the largest structure we know of. The universe, on the largest scales, is organized into what astronomers call the cosmic web, a vast, three-dimensional network of filaments and sheets and voids that gives the universe a structure resembling, eerily and for reasons that are not fully understood, the structure of neural networks in the brain. The filaments are long strands of galaxies and dark matter, stretched across hundreds of millions of light-years, connected at dense nodes where galaxy clusters pile up like rush-hour traffic at intersections. Between the filaments are the voids, enormous regions of space containing almost no galaxies at all, empty bubbles hundreds of millions of light-years across, separated from the next void by thin sheets of galaxy clustering. The Sloan Great Wall, identified from data gathered by the Sloan Digital Sky Survey, is a filament of galaxy superclusters stretching approximately 1.4 billion light-years from end to end. Yet it was, for a time, considered the largest known structure in the observable universe. Then, in 2013, a team of astronomers identified a possible structure they named the Hercules Corona Borealis Great Wall, a concentration of gamma-ray bursts spanning an estimated 10 billion light-years. If confirmed as a true large-scale structure, it would be roughly 1/10 the diameter of the entire observable universe, a single coherent structure 1/10 the size of everything we can see. On our dinner plate model, the Hercules Corona Borealis Great Wall, if it is real, would span approximately 2.5 million kilometers. That is more than 6 times the distance from the Earth to the Moon. A structure that, a model where the Milky Way fits on a dinner plate, requires a gap between Earth and Moon to contain. Yes, and still we have not reached the edge. The observable universe, the sphere of space from which light has had time to reach us in the 13.8 billion years since the Big Bang, is approximately 93 billion light-years in diameter, not 13.8 billion. The universe has been expanding while that light traveled, so the objects whose ancient light we now receive have been carried by expansion to positions far beyond where they were when they emitted it. The observable universe is 93 billion light-years wide, containing an estimated 2 trillion galaxies, and more stars than there are grains of sand on every beach and desert on the surface of Earth. 2 trillion galaxies, each containing hundreds of billions of stars, each star potentially surrounded by planets, and we on one of those planets. But on one of those stars, in one of those galaxies, somewhere in the outer edge of a supercluster that is itself a minor suburb of the cosmic web, we are asking where we are. The answer, in pure geometric terms, is almost nowhere. The volume of space occupied by the Earth, measured as a fraction of the volume of the observable universe, is a number so small that it has no practical meaning. The Earth is to the observable universe what a single atom is to the Earth, and then less than that. If you took the observable universe and compressed it to the size of the Earth, the actual Earth would be far smaller than any particle physics experiment has ever detected. It would not be an atom. It would not be a proton. It would be something smaller than the theoretical minimum length that physics currently recognizes as meaningful. We are nothing. In spatial terms, the numbers make this unavoidable. And yet something strange happens when you sit with this for a while, when you let it settle rather than immediately reaching for comfort. The smallness is real. The numbers are correct. But they are not the whole story, because mixed in with the vertiginous arithmetic of scale is a different kind of fact. A fact not about size, but about complexity. Not about extent, but about what that extent contains, and what, against all reasonable expectation, has emerged within it. Consider the hierarchy of structures we have passed through on this journey. Atoms, forming molecules. Molecules forming rocky planets warmed by nearby stars, developing chemistry complex enough to become biology. Biology over billions of years of evolution by natural selection. Thus developing nervous systems growing more complex over millions of years, developing brains capable of memory, prediction, communication, and eventually of science, of constructing, from careful observation and precise measurement, a description of the universe accurate enough to reveal the universe's own structure. The universe built something capable of seeing itself. The atoms that the Big Bang produced, the hydrogen and helium that gravity compressed into stars, the heavier elements that stellar fusion and supernova explosions scattered across space, some of those atoms, in some places, under some conditions, arrange themselves into structures that can look outward and understand the arrangement. That is not a small thing. That may be the most remarkable thing the universe has ever produced. Now, regardless of how small a fraction of its volume those structures occupy. Carl Sagan wrote that we are a way for the cosmos to know itself. He meant this not as poetry, or not only as poetry, but as a statement of genuine physical fact. The universe is old. It has been here for nearly 14 billion years. For most of that time, for almost all of that time, nothing in it knew anything. Stars burned without being observed. Galaxies collided in silence. The cosmic web spread across billions of light years with no eye to witness its architecture and no mind to name its structures. And then, in certain places, in certain moments, in the thin biospheres of certain rocky planets around certain stars, the matter of the universe began to reflect on itself. To count and measure and be astonished, we are that reflection, brief, local, improbable. But real. There is something else worth considering in the context of scale, something that the numbers of size and distance inevitably lead toward when followed honestly. The universe is not just large in space, it is large in time. It has existed for 13.8 billion years. The Earth has existed for 4.5 billion of those years. Life on Earth has existed for about 3.8 billion years. Complex animal life, the kind with eyes and nervous systems and mobility and behavior, has existed for roughly 600 million years. Mammals have existed for about 220 million years. Hominids, the family of primates that includes us, have been around for about 7 million years. Anatomically modern humans have existed for roughly 300,000 years. Civilization, agriculture, writing, cities, the accumulated and transmissible knowledge that makes science possible, is approximately 10,000 years old. In the timeline of the universe, 10,000 years is nothing. It is less than 1/1,000,000th of 1% of the age of the cosmos. If the entire history of the universe were compressed into a single calendar year, civilization would appear in the last fraction of the last second of December 31st. The Egyptian pyramids, which feel ancient to us, would be separated from the present moment by less than the blink of an eye. The entire span of recorded human history, everything we know happened, every war and discovery and work of art and scientific breakthrough, occupies a period so small on the cosmic calendar that no analogy I can offer will make it feel as small as it really is. And within that tiny sliver, within those 10,000 years of civilization, the period during which humanity has been able to measure and understand the scale of the universe is smaller still. The realization that the Milky Way is a galaxy, one of many, not the totality of all stars, came only in the 1920s, when astronomer Edwin Hubble measured the distance to what were then called spiral nebulae and found them to be far beyond the boundaries of our own galaxy. Before that, within living memory of people alive today's grandparents, humanity didn't know that other galaxies existed. The discovery that the universe is expanding, that the distances between galaxies are growing, that the cosmos had a beginning in a hot, dense state we now call the Big Bang, came in 1929 from Hubble's observations of galactic recession. The cosmic microwave background radiation, the direct observational evidence for the Big Bang, was discovered accidentally in 1965. The accelerating expansion of the universe, the finding that dark energy is pushing space apart at an increasing rate, was discovered only in 1998. The identification of Laniakea as the supercluster complex containing our galaxy was published in 2014. We have understood the basic architecture of the universe for less than 100 years. The largest structures in the cosmos were named and described within the lifetimes of people alive today. We are extraordinarily new to this knowledge. We have barely begun. And this newness is not a failing. It is a condition of our position in cosmic history, a position that is, by the standards of the universe, almost impossibly early. The sun will continue to shine for approximately another 5 billion years before exhausting its hydrogen fuel. The last red dwarf stars will continue to burn very slowly for trillions of years beyond that. On the timescale of all the life that could ever exist in this universe, all the civilizations that might arise around all the stars that have not yet formed, we are among the first. We are the early ones, the ones who got here while the architecture was still being mapped, who looked up before the full picture was in focus. This is both humbling and, if you are willing to hold it at the right angle, extraordinary. To be among the first to understand the scale of the thing you are inside, to be the first arrangement of matter in this corner of the universe. Yes, to grasp the size of the cosmos that made you is a privilege so strange and so unlikely that the universe went nearly 14 billion years without producing it even once, as far as we know. The Andromeda galaxy is heading toward us. That much is real. In approximately 4.5 billion years, the gravitational pull between Andromeda and the Milky Way will have drawn them into a collision. Not the violent explosive collision that word implies, but a slow gravitational dance, two vast collections of stars passing through each other over hundreds of millions of years. They're stars so widely spaced that direct stellar collisions will be rare. The two galaxies will eventually merge into a single large elliptical galaxy. The night sky for any beings that exist to observe it. It will transform over those millions of years into something no human eye has ever seen. A sky dominated by the blaze of stellar nurseries, newly formed stars lighting up the galaxy merger from horizon to horizon. We will not see it. The sun will be dead before it happens. Whatever we are, in 4.5 billion years, if anything remains of us at all, will be something we cannot imagine from here. But right now, in this particular sliver of time, on this particular small rock, around this particular medium star, in this particular outer arm of this particular spiral galaxy, which is itself one of 100,000 galaxies falling slowly toward the great attractor inside an immense structure named for the open sky. Right now, we are here. We are awake. We are measuring. The observable universe is 93 billion light-years across. It contains 2 trillion galaxies. It is 13.8 billion years old. It is made mostly of things we cannot see. Dark matter, which provides the gravitational scaffolding for all visible structure, and dark energy, which drives the accelerating expansion that will eventually carry most of those 2 trillion galaxies beyond our cosmic horizon forever. And somewhere in all of that, smaller on a cosmic scale than any physical analogy can convey, is a planet. Warmed by a star, wrapped in a thin shell of nitrogen and oxygen, covered in liquid water, alive with chemistry complex enough to have produced in the time available, things that breathe and move and think and look up. That planet is here. You are on it. Yet, and you are made of the same atoms as everything else in the universe, the same hydrogen produced in the Big Bang, the same carbon and oxygen and iron scattered by exploding stars, the same ancient material that forms the cores of distant galaxies, and the dust between them. There is no meaningful chemical distinction between you and a nebula. The difference is arrangement. The difference is that here, in this arrangement, the atoms look outward and recognize themselves. The universe is incomprehensibly vast. We are incomprehensibly small, and we know it. We have measured it. We have built the mathematics to describe it and the instruments to confirm the description. We have done, from our tiny position on our tiny rock, something the universe went nearly 14 billion years without doing anywhere we can see. And we have understood where we are. That understanding does not make us larger. It does not reduce the distances or soften the numbers. The scale is what it is, and it is enormous, and we are small within it in ways that no encouragement can change. But it makes us something specific, something the universe, for all its vast and silent machinery, had to work at for almost 14 billion years to produce. Look up tonight, if you can. The stars you see are close ones, the neighborhood, cosmically speaking. The smudge of the Milky Way overhead, if you are somewhere dark enough to see it, is your galaxy's plane seen edge-on, 100,000 light-years of stars compressed to a band of pale light. The faint oval of Andromeda, if you know where to look, and is 2.5 million years of light arriving at your eye from 1 trillion distant suns. All of that, all of it, the whole vast, cold, ancient, expanding structure of the cosmos is what it took to make the moment you are in right now. All of those atoms, all of those stars, All of those billions of years of physics operating without witness. And now, you, here, awake, looking up. It is terrifying, yes. The scale is genuinely terrifying, but it is also the most extraordinary thing that has ever happened in this part of the universe. You are very small, and you are here. And against all odds, you understand exactly how small you are. That might be everything.